Hey guys, today we're going to learn how to calculate limits that involve absolute value functions. Now let's look at what an absolute value function looks like. All absolute value functions look like a V. And actually an absolute value function is a piecewise function in disguise. So let's look at the absolute value of x. This can be broken down to two pieces where we have negative x for when x is less than 0. As you can see here, we have this line which is going down. So that's why the slope here of that line is negative. And for when x is less than 0, because at 0 is when it switches to a positive slope. So the line is increasing here like that. So absolute value can be written as these two pieces. When we're trying to calculate a limit of an absolute value function, it's important that we first break up the limit into its one-sided limits using the piecewise function. So if I were to calculate the limit as x is approaching 0 from the left, I would use the top piece because that is when x is less than 0. So 0 from the left would equal to 0. And then the limit as x is approaching 0 from the right would also equal to 0. And this is because at x is equal to 0, that's where we have the vertex of the graph where the line splits. Now the reason why we do this and we get the absolute value and we split it into its pieces, because if I were just to use direct substitution, then our y values, anything that comes out of the absolute value would end up being positive. But what if it was negative? So we always need to split it. Let's look at how we would accomplish that. So let's say I wanted to calculate this limit. The limit as x is approaching negative 2 from the left, and we have the absolute value of 2x plus 4. So we have these two limits, the limit as x approaches negative 2 from the left and from the right. So my first step would be to take my absolute value and rewrite it as a piecewise function. For your convenience, I have the steps here on how you can rewrite it as a piecewise function. The first part is to take your absolute value part, whatever is inside of it, and we're going to make it greater than or equal to 0. This will account for the positive side of the graph. That's why it's greater than or equal to 0. And what we're doing is we're first calculating where it is that my graph will split from the negative slope to the positive slope. So we solve for x to get that inequality. Here we get 2x is greater than or equal to negative 4, and then we divide by 2. So x is greater than or equal to negative 2. Once we have this is basically the vertex of the absolute value. That's where it splits up into its two separate lines. So to write our piecewise function, this is for the right side. So we're going to take whatever is inside of the absolute value, 2x plus 4, and we make it for when it's greater than or equal to negative 2. To get for the other side, we're going to make it negative because then the slope is opposite. And then for the inequality, it would be x, and we're going to switch the inequality symbol, so less than negative 2. Since it's already included here, I don't need to include it here. So the first one is always greater than or equal to, and then the second one, we switch the sign. So now if I want to calculate the limit as x approaches negative 2 from the left would be this bottom equation here, because this is when x is less than negative 2. So I am going to use that equation to then plug in the negative 2. So we get 2 times negative 2, which is negative 4, plus 4, which gives me 0. So negative 0 is just 0. Then we do it from the right. So the limit as x approaches negative 2 from the right side, we're going to plug it in, and we get, because this is the right, we're going to use the top one. So this would be 2 times negative 2 plus 4, which also gives me 0. So if I was asking for the general limit, They both equal to 0, so we would say that the general limit as x approaches -2 would equal to 0. Now let's look at some other examples here. We have the limit as x approaches -1 of 9x plus 2. So first we need to rewrite this as our piecewise function. So I'm going to take that 9x plus 2 and make it greater than or equal to 0 to solve for when my absolute value would split. So we subtract the 2, so 9x is greater than or equal to -2, and then divide the 9. So x has to be greater than or equal to -2/9 for the positive version of my absolute value. So this is my pieces. We have the 9x plus 2 for when x is greater than or equal to -2/9. And then we have negative 9x plus 2. And now we switch the inequality symbol, so x is less than -2/9. Now we look at the limit. This is for when x is approaching -1. -1 is less than -2/9. So I would have to use this bottom piece here. Now notice what happened, right? If I had plugged in -1 directly into the absolute value, I would end up with a positive number. But as you can see here, since x is less than -1 and I have to use the bottom, we're most likely going to end up with a negative or the opposite sign. So let's go ahead and figure that out. So we have -9 times -1 plus 2. 9 times -1 is -7. -7 plus, I'm sorry, -9. -9 plus 2 is -7. And we end up with 7. Now, if I had plugged in -1 here, I would end up with the same answer. So in this case, we didn't necessarily need to go through this, but that doesn't work for all of the absolute value functions. So it's better to be safe than sorry, right? We were always going to split up the absolute value into its pieces and then evaluate the limit. Let's look at this next one here. We have the limit as x approaches -8 of 1 plus 4x. So I'm going to take my absolute value and find that inequality. So make it greater than or equal to 0. Subtract the 1, so 4x is greater than or equal to -1. And then divide the 4, so x is greater than or equal to -1/4. So this is going to be my pieces. We have 1 plus 4x for when x is greater than or equal to -1/4, and then -1 plus 4x for when x is less than -1/4. So we're evaluating for the limit as x is approaching -8, which is less than -1/4. So we're going to use this bottom piece here. So -1 plus 4 times -8. This is -32 plus 1, which is -31. And -31 is equal to +31. Now let's look at this one over here. We have the limit as x is approaching -3 of absolute value of -5x minus 9. So we're going to take that -5x minus 9 and find our first inequality. Add the 9, so we get -5x is greater than or equal to 9, and then divide by -5. Now remember, when you are working with inequalities, if you ever divide or multiply by a negative across the inequality, that inequality symbol will change signs or will change direction. So x is going to be less than or equal to -5/9. So this is for the positive version of my inequality still. Or rather, it's for the left side, but we're still going to take, we still follow the same steps when we're writing our pieces. So the first piece, we just take whatever is inside of the absolute value and copy this inequality we solved for. So x is less than or equal to -5/9. And then now it's going to be -5x minus 9. and we switch that inequality symbol. So this will now be greater than negative 5 over 9. Now negative 3 is less than negative 5 over 9. So when I look at my pieces here, it's the top side that is less than that negative 3 will fit into. So we're going to plug it into the top here. So negative 5 times negative 3 minus 9. Negative 5 times negative 3 is 15. And 15 minus 9 would equal to 4. Our last one here, we have the limit as x is approaching 3. So we're going to do the same thing here. Let's find our first inequality. We make this greater than or equal to 0. Now you can add the x or you can add the 1 and then divide. That's up to you. I'm going to add the 1. So negative x is greater than or equal to 1. And then I'm going to divide by negative 1, which will also switch my inequality symbol. So for my pieces, my first piece is negative 1 minus x for when x is less than or equal to negative 1. And then my bottom piece is going to be negative 1 minus x for when x is greater than or equal, I'm sorry, not equal to, just greater than negative 1. Now 3 is greater. So I am going to use this bottom piece here. So we have negative 1 minus 3, which is going to equal to negative 4, which equals to 4. Now all of these happen to work out that we always ended up with a positive number. But let's say if the limit for b, instead of approaching negative 3, it was negative 1. Let's try that a second. If it was negative 1, then that means I would have had to plug it in to this top version right here, since negative 1 is less than negative 5 over 9. So if I plug it in, I would get negative 5 minus 1 times negative 1 minus 9. This will give me positive 5 minus 9, which equals to negative 4. So if I had just plugged in negative 1 here, I would have gotten the absolute value of negative 4, which would equal to positive 4. So that's why direct substitution doesn't always work for absolute value and why we have to split it up into its pieces. Now let's look at when we are trying to evaluate an absolute value function where it's actually also a rational function. So for example, in this first one, we have the limit as x is approaching 1 of the absolute value of x minus 1 over x minus 1. We first have to take that absolute value part only and rewrite it using our pieces. So let's set up for that inequality. We have x minus 1 is going to be greater than or equal to 0. Add the 1, we have x is greater than or equal to 1. So my pieces for the absolute value would be x minus 1 for when x is greater than or equal to 1, and negative x minus 1 for when x is less than 1. So this is a general limit. So we want to make sure that the left side is going to equal to the right side. So we have to break this limit up into its two parts. We're going to first start with the limit as x is approaching 1 from the left, which from the left would be the bottom piece here, because that's where x is less than 1, so that's the left side of 1. So negative x minus 1 over x minus 1. The x minus 1's would cancel, and I'm left with negative 1. Now let's do the right side. The limit as x is approaching 1 from the right would be now the top piece, because this is for when x is greater than 1, so the right side. So that would be x minus 1 over x minus 1, which these would cancel, and I'm left with 1. So essentially, when you're rewriting your limits, your one-sided limits of absolute value, you replace the absolute value with the one-sided part from your piecewise function. So now the general limit, as you can see, these one-sided limits do not approach the same number. So for my general limit, as x is approaching 1 of the absolute value of x minus 1 over x minus 1 does not exist. Let's look at this next one here. Now this is a one-sided limit, so we will get an answer. We have the limit as x is approaching negative 6 from the right of 2x plus 12 over the absolute value of x plus 6. So let's find the piecewise function for the absolute value. So I'm going to set up my inequality. Subtract the 6, we get x is greater than or equal to negative 6. So my pieces, the first one is x plus 6 for when x is greater than or equal to negative 6. And then the bottom would be negative x plus 6 for when x is less than negative 6. So now we're trying to evaluate the limit as x approaches negative 6 from the right of 2x plus 12 over the absolute value of x plus 6. Now this is from the right side. So the right side of negative 6 would be the positive x plus 6. Now here I would have to factor to be able to find this answer because I can't just plug in the negative 6 since that would give me 0 in the denominator. But if I factor the numerator, I have 2x plus 6 over x plus 6, which the x plus 6's would cancel, and I'm left with an answer of 2. Let's try a couple more. For this first one, we have the limit as x is approaching 0 from the left of 1 over x minus 1 over the absolute value of x. So let's write our pieces for the absolute value of x. So my inequality is just going to be x is greater than or equal to 0. And there's nothing to solve for, so this is it. So my pieces, we have the positive, so x for when x is greater than or equal to 0, and then negative x for when x is less than 0. Now, let's go ahead and replace the absolute value with the appropriate piece. This is from the left, so I'm going to use this bottom one here. So 1 over x minus 1 over negative x, which here negative and negative will become positive, so 1 over x plus 1 over x. Now when we add, the denominators are the same, so we're going to add the numerators. 1 plus 1 is 2 over x. Now I can't do anything else with this, and I can't just plug in 0 because I would get 0 in the denominator, meaning that there's a vertical asymptote. So this is a one-sided limit though, so I do need an answer. So I'm going to plug in a number slightly to the left of 0 in order to figure out which infinity it's going to be. Since remember, this is a vertical asymptote, so my graph is going to approach either positive infinity or negative infinity. So we have 2 in the numerator, which is a positive number, over, if I plug in, let's say, negative 0.1, we would get a negative. And a positive divided by a negative would give me negative infinity. Now let's look at B. This is a general limit, meaning that I need the left side to equal to the right side. The absolute value part is the same as this one up here, so we already wrote our pieces. So let's do the left. The limit as x is approaching 0 from the left would be x over x minus, and the left would be negative x, so we'll put plus x, because x minus negative x will become positive. This is equal to x over 2x. My x's would cancel, and I get 1/2. Now let's do the right. The limit as x approaches 0 from the right. If it's from the right, I would replace it with x over x minus positive x, which is just x. So this gives me x over 0. Something's going on there and it's not right because this is undefined or does not exist. So regardless, the left side doesn't equal to the right side. So the general limit as x is approaching 0 of x over x minus the absolute value of x does not exist. Now let's look at C. We have the limit as x is approaching 7 from the right. So of 7 minus x over absolute value of x minus 7. So let's break this down into our pieces. We have x minus 7 is greater than or equal to 0. Add the 7, so x is greater than or equal to 7. So our pieces here, x minus 7 for when x is greater than or equal to 7, and negative x minus 7 for when x is less than 7. So let's write out our limit. As x approaches 7 from the right would be 7 minus x over the right side would be this top one here, so x minus 7. Now what I notice here is that everything from the numerator and the denominator, they're the same elements, but they're different signs. Here the 7 is positive where it's negative in the denominator. Here the x is negative where it's positive in the denominator. I want to be able to cancel them out. Since x is approaching 7, I can't exactly plug that in. So what I can do is factor out a negative from either the numerator or the denominator. I'm going to factor a negative from the numerator, which will then turn this 7 negative and the x positive. Which, even though this is written in a different order, it's the same as the x minus 7. Because see, negative 7, positive x. So I can cancel these out, and I'm left with my answer of negative 1. Now let's look at this last one. This is a general limit, so I need to find both the left and the right and make sure that they both approach the same number. So let's write our first inequality. We have 1 minus x is greater than or equal to 0. Subtract the 1, we get negative x is greater than or equal to negative 1. And then divide by negative 1, which will make my inequality x is less than or equal to positive 1. So this is for our positive version of the absolute value. So that's our first piece, 1 minus x for when x is less than or equal to 1, and then negative 1 minus x for when x is greater than 1. So let's find the left side limit. The limit as x is approaching 1 from the left would be the 1 minus x squared over, now the left is the top piece, so that is the 1 minus x. Now what I can do with the 1 minus x squared is that this is a difference of squares. So we get 1 minus x times 1 plus x. And in the denominator, it's 1 minus x. So I can cancel. And now I can plug in the 1. So 1 plus 1 would equal to 2. So this is my left limit. Now let's do the right limit. So we still have the 1 minus x squared. I'm just going to already write it factored out. Over, and instead of 1 minus x, it would be negative 1 minus x. I can cancel these 1 minus x's, and I get 1 plus x over negative 1, which we can leave like this. You can put the negative on the side. That's up to you. But I'm just going to plug in the number. So this would be 1 plus 1 divided by negative 1, which gives me negative 2. So since the left does not equal to the right, then this particular limit does not exist. And that's limits of absolute value functions.